Hello everyone, my name is Daphne Gonzalez. Today I will present to all of you this work called Microstructural Correlation of Pipeline Grade Steels with Susceptibility to Stress Corrosion Cracking. First of all, I will give you a small introduction why we did this work. Well, in the petroleum industry, the transportation of hydrocarbon is done using low carbon pipeline grade steels due to economic and safety reasons. However, pipelines are always exposed to different types of damage, with stress corrosion cracking being one of them. Stress corrosion cracking is a phenomenon that is commonly observed in high pH environments. However, studies have shown that it can also occur in environments with near neutral pH. This type of stress corrosion cracking is known as non-classical stress corrosion cracking and has been studied to a lesser extent, which is why this work addresses the occurrence of this phenomenon in a near-neutral pH environment. Due, due to stress corrosion cracking is a combination of material, environment, and load, this work evaluates the effect of microstructural characteristics on susceptibility to stress corrosion cracking using two pipe segments with API 5L X56 and X60 specifications in an NS4 with near neutral pH solution while performing a 3-point bending test. And how we did this study for this phenomena? Well, the experimental methodology employed first involved performing metallurgical and mechanical characterization of each one of the steels used, which met the specifications described for API 5L X 56 and 60 respectively. Once the test steels were evaluated, they were subjected to an SEC testing model for 6 months, as is described in the ANSI TM0177 standard, which also describes the 3-point bending method for specimens. Each steel was evaluated with different load percentage relative to the yield strength of each material. The test environment was an S4 solution with a near neutral pH in an autoclave for at 80 Celsius degrees, more or less 5 Celsius degrees. The solution was purged with a gas mixture of 5% of carbon dioxide and 90% of nitrogen. After the 6-month testing period, the samples were removed from the autoclave and a pit count was performed for evaluation. Subsequently, these pits were examined using scanning and electron microscopy. Well, as I said before, the most important thing to this work was evaluate the differences microstructurally that can affect a material to get a susceptibility to SEC. So the materials used were extracted from decommissioned pipelines. After metallurgical and mechanical characterization, the main difference between them were identified, which served to analyze the result of this research. The X50 six steel was the steel number one, showed lower content of carbon, perlite, and inclusions. However, its grain size was large compared to the X60 steel, which, as seen in the image, has a greater homogeneity in microstructure as well as more well-defined perlite colonies. Now, what were the results we obtained? Since pits are nucleation sites for cracks, a count was performed on each specimen. It was observed that in both steels, the number of pits increased with the applied load. The higher load, the greater the number of pits. Additionally, the load condition, whether in tension or compression, was evaluated, and it was found that the load points in 3-point bending test act as the the concentrators where the higher number of pits colonies were located. The pits found in the sample lacked the typical morphology of pits caused by electrochemical corrosion. SEC-induced pits showed greater dissolution inside them and did not have a spherical morphology. Subsequently, we evaluate the pits with scanning electron microscopy to confirm the occurrence of ACC-induced cracks. It was found that the crack formation occurred in both steels with transgranular cracks. This transgranular is characteristic of non-classical ACC, being more predominant in the steel number 2, that is the X60 steel. So finally, what were the conclusions and analysis we made for these studies? Well, the results show that the formation of the pit with atypical morphology with cracks observed at their base indicates the initiation of the stress corrosion cracking mechanism. It also was observed that a higher content of paralytic microconstituent and greater homogeneity in the microstructure reduced the formation of these pits. Additionally, it was found that the magnitude of the applied stress directly influences the occurrence of pits, with a higher frequency at greater stress levels. The evidence obtained, both photographic and microscopic, allow us to identify that the generated cracks are associated with non-classical stress corrosion cracking that is characterized by transgranular propagation and their location at the base of the pit with atypical morphology. I appreciate all the interest you have shown in this work. I hope you liked it.